Hello and welcome to my YouTube channel. Today I shall be treating part 1 of the topic Inequalities. Please kindly subscribe to this channel if you've not done so already. Definition: an inequality is an algebraic expression connected by any of the following order relations: less than, greater than, less than or equal to, greater than or equal to, or not equal to. So whenever we see an expression that are connected with any of these other relations, that qualifies that expression to be an inequality. Examples of inequality include the following. 1. The expression x plus 5 less than 3. So here we have used the relation less than, and that makes it an inequality. Another example is the expression y squared minus 3y minus 4 greater than or equal to 0. Once again, we have made use of another relation here, greater than or equal to 0. That makes that expression an inequality. Another example could be 3x plus y not equal to 0. Once again, we have used other relation here, not equal to, and that makes it an inequality. In other words, whenever we do not make use of the sign equal, what we're dealing with must be an inequality. If this were to be an equation, then it would have been y squared minus 3y minus 4 equal to 0. This makes this an equation. So whenever we are not using this equality sign, we should be making use of either less than, greater than, less than or equal to, or any of these other relations. And that would mean that we are dealing with inequalities. So in this topic, we'll be dealing with expressions or algebraic expressions that are connected, by any of these other relations. Now let's talk about solution of inequalities. While a linear equation always has one unique solution, a linear inequality has infinitely many solutions. I'd like to explain this with an example. If we are given the equation 2x minus 3 equal to 1, say to solve, we will now say that 2x is equal to 1 plus 3. We'll now say that 2x is equal to 4. So when we divide both sides by 2, we have that x is equal to 2. Now, since this is a linear equation, it would mean that x equal to 2 is the only solution to the linear equation. X equal to 2 is not just the only solution, it is a unique solution in the sense that there is no other solution to the linear equation we have just solved. In other words, it means that x equal to 2 is the only value of x that satisfies the equation. What do we mean by satisfying the equation? That if we plug in the value x equal to 2 into this equation, into the left hand side of the equation, then we shall end up with the right hand side. Let us see. X equal to 2. So we go back here. 2 into x is 2. So we put 2 here minus 3. So 2 times 2 is 4 minus 3. And 4 minus 3 is 1. And 1 is what we have on the right hand side. So when we substitute the value we have obtained into an equation and we get the value of the right hand side, we will now see that that value satisfies the equation, hence a solution to that equation. Now what we are saying here is this. For a linear equation such as this and many more, there can be only one unique solution, just like we have seen here. However, if we transform this equation to be an inequality with any of the other relations we had discussed earlier, for example, if this becomes 2x minus 3 less than 1, this changes from being an equation to an inequality because we now have the other relation here, less than. So if we attempt to solve this, let's see where we arrive at. We have 2x less than 1 plus 3, in the same way we had solved the linear equation. We now have 2x is less than what? 4. If we divide both sides by 2, we get that x is less than 2. We had x equal to 2 as the only solution in the linear case. And now we have x is less than 2 as a solution, as one solution of the inequality 2x minus 3 is less than 1. The fact that x is less than 1 means that all values of all values less than 2 are solutions of the inequality. Let us see. For example, 1 is clearly less than 2. Let us see if 1 satisfies inequality. So if we put 1 here, 2 times 1 minus 3. 2 times 1 is 2 minus 3. And 2 minus 3 is equal to negative 1. And clearly, negative 1 is less than 1. So 1 is one of the solutions of the inequality. Let us check another value, 0. Obviously, 0 is less than 2. So when we substitute the value of 0 into inequality, let's see what we have. We have 2 into 0, 2 times 0 minus 3. So 2 times 0 is 0, and 0 minus 3 is negative 3. And once again, negative 3 is less than 1. So negative 3 is also a solution to the inequality 2x minus 3 is less than 1. What then is the major difference? While a linear equation has just one unique solution, an inequality usually has many solutions, or we say that it has infinitely many solutions. So what this simply means is that all values of x that are less than 2 are solutions of the inequality. So for this reason, when talking about solution of inequalities, we often speak of solution sets. So the solution set, therefore, of an inequality would now be those values of the variable x in this case, which makes rather the statement or the inequality to be true at all times. We'll now take some good examples of inequalities and then show how to represent the solutions as sets. Example: find the solution set of the following inequalities and represent them using the number line, set notations, and intervals. So we're going to solve these three inequalities here and represent the solutions in three different ways. We represent them using number lines, represent them using set notations, and also represent them using intervals. Number one, we have 2x minus 7 greater than 3. So if we solve this, this is 2x, this is minus 7. If we add 7 to both sides, or if you like, this is minus 7 to the right hand side becomes plus 7. So we have 2x greater than 3 plus 7. So that 2x is greater than what? 10. If we divide both sides then by 2, we have that x is greater than what? 5. So x greater than 5 becomes a solution of the inequality. But recall that this simply means that all values of the variable x that are greater than 5 are solutions to the inequality. Now we'll now represent this solution on a number line and see how it looks. So we have a number line here. This goes to plus infinity. The left side goes to negative infinity. And x is greater than 5. So 5 is somewhere here. Now we draw a ball just above 5. Greater than 5. All values that are greater than 5 are values that lie to the right hand side of 5. Values like 5.5, 5.2 are all bigger than 5. 6, 7, 8, and they are all to the right of 5. So using a number line, we simply draw a line with an arrow pointing to the right. Now this will simply mean that all values of x that are greater than 5 are solutions to the inequality. Now you also take note here of the fact that this ball here has not been shaded, it's left unshaded, and that is because the inequality here is strict. We said x is strictly greater than 5. What this implies is that in the solution region, 5 is not one of the solutions. That is because the inequality is strict. We can even check to see that indeed 5 is not in the solution set. If we substitute 5 into the inequality, we have, this is 2x is 5, 2 times 5 is 10, and 10 minus 7 is 3. So we'll now be having 3 greater than 3, which is not true, because 3 is not greater than 3, rather 3 is equal to 3. So this means that 5 is excluded from our solution set. That's the solution we have expressed or we have represented using a number line. Now to represent the solution using set notations, what are we saying? We are saying that all values of x that lie between 5 and infinity are in the solution region of this inequality. So in set notation, we simply say that all values of x that lie between infinity and 5 are in the solution set. So what we have represented here using a number line is the same thing we have done using set notations. So this simply means that the solution of the given inequality are all values of x that are all less than infinity. Of course, they are all less than infinity because you can't get to infinity. They are all less than infinity and they are all greater than 5. So they are all bigger than 5 means that 5 is less than x and x is less than infinity. And from the number line here, it's obvious that all those values lie between 5 and infinity. Lastly, in terms of intervals, we will write that x belongs to the following interval. Now, since we have here 5 and infinity, now observe this. Since 5 is not in the solution set, and I have explained why it's so, because when you substitute the value of 5 into the inequality, we have 3 greater than 3, which is not true. So the number 5 is not in the solution set. For that reason, we now use this type of open bracket around 5. There's another kind of bracket that can be used, which we shall see later. And that bracket is this way, the straight bracket. Now this bracket is used because 5 is not in the solution set of our inequality. For that reason, we will say that this inequality, that this interval rather, is a left open interval. So if we had used this, we would have said that the interval is left closed. So this means left open. Now let us talk about infinity. Whenever we have infinity, the interval, the right hand side or the side to infinity is always open. Since infinity is not a number that we can reach, so it is impossible to close at infinity. So wherever we have infinity, we always close. Now on this interval rather, the interval is open at 5, and of course it will always be open at infinity. Therefore, the left hand side is open, the right hand side is open. Since both sides of the interval are open, we call this kind of interval an open interval. We call it an open interval. Therefore, an open interval is an interval that is left open and also right open. We call it an open interval. So this simply means that x belongs to this interval. That means all solutions to the inequality we have solved belong on the interval 5, the open interval 5 and infinity. This interval is a solution to the problem, and it's the same thing as this set notation is also the same thing as what I've represented on the number line. Number 2, we to find the solution set of the inequality 5 minus 2x less than or equal to 0. So let us solve this again. So this is minus 2x less than or equal to, this is plus 5, to the right it becomes negative 5. Now to get the value of x, we have to divide both sides by negative 2. Now take note of this at this point. Whenever we divide both sides of our inequality or multiply both sides of our inequality by a negative sign, the sign of the inequality changes. In other words, if we divide both sides by minus 2, divide here by minus 2, we will now have that x, instead of being less than or equal to, becomes greater than or equal to 5 over 2. So take note, whenever we multiply both sides of our inequality or divide both sides of our inequality by a negative sign, the inequality changes its sign. And the reason is very simple. Take for instance, minus 2 is less than 1. This statement is true because negative 2 is less than 1. But if we multiply both sides of this inequality by negative 1, what do we get? Minus 1 times minus 2 becomes 2, and then minus 1 times 1 becomes minus 1. And when this becomes this, it now becomes obvious that 2 becomes greater than minus 1. So because we have multiplied both sides of the inequality by a negative sign, the order, the sign of the inequality has to be changed to the reverse 1. So minus 1 is less than 1, but 2 is greater than what? Minus 1. In the same way, that's what we have done here. So this applies when you're multiplying both sides, by a negative number, or when you're dividing both sides by a negative number. You take note of this, that the sign of the inequality changes. So back to the example. We have that x is greater than or equal to 5 over 2, which simply means that x is greater than or equal to what? 2.5. So that is the solution to inequality. And what does this mean? It simply means that all values of x that are greater than or equal to 2.5 are in the solution set of this inequality. We have to take note of something here. In the previous example, what we had was strictly greater than. But what we have here is not strict. We say greater than or equal to. So in that case, it would mean that the solution begins from 2.5. When we had x greater than 5, it meant that the solution began after 5. But now we have x is greater than or equal to 2.5. This means that the solution begins at 2.5 and to the right. Now let's represent the solution on a number line and see how it looks. Our number line once again. Remember that to the right of the number line is plus infinity. We'll just write infinity. And to the left of the number line is negative what? Infinity. So 2.5 is just, let's say, somewhere here. 2.5 is somewhere there. And we open up a ball, above 2.5. The next question is, should we draw our directed line to the right of 2.5 or to the left of 2.5? We come back to check. We said x is greater than or equal to 2.5. Now, values that are bigger than 2.5 must lie to the right-hand side of 2.5. So we draw our line this way with an arrowhead. This simply means that all the values to the right of 2.5 are in the solution set of our given inequality. Again, our inequality here is not strict. We have greater than or equal to. For that reason, we now shade the ball above 2.5. And what this tells us is that the solution region of the inequality begins from 2.5 and all other values above 2.5. So if you substitute this value of 2.5 into the inequality, you find out that the inequality will be satisfied. Let us see. If we put 2.5 here, we simply get what? We get 5 minus 2 times 2.5. That gives us 5 minus 2 times 2.5 is 5. And 5 minus 5 is what? Is 0. And we said here that 5 minus 2x is less than or equal to 0. And in this case, we have 0. 0 is not less than 0, but 0 is equal to 0. Hence, 2.5 is also a solution to the inequality given to us. Every other value that is greater than 2.5 will also be a solution to the inequality. And of course, 2.5 and above, from 2.5 to wherever it is that you call infinity. And bear in mind that infinity has no end. To represent the solution now, in terms of set notation, what then do we write? What this means is that all the values of x from the given problem, all the values of x that lie between 2.5 and infinity are in the solution region. So I'll simply write that x that lies between infinity and 2.5 are in the solution region. But recall that we have explained already here that 2.5 is also in the solution region. Hence, instead of saying less than, we'll say less than or equal to. Note, when you say 2.5 is less than or equal to, you are also saying that x is greater than or equal to 2.5. So this statement is here already. So I have represented the same solution here on a number line. Here we have done it, in terms of set notation. How then do we represent it using, our intervals? Remember, we have that x lies in the interval. This is infinity, and I've said already that at infinity you can never close. You always have an open interval at infinity. Now how about 2.5? We have here 2.5 comma infinity. Now should we open at 2.5 or close at 2.5? That will depend on if 2.5 is also in the solution set or not. We go back to our inequality. The solution says that x is greater than or equal to 2.5, meaning that our solution begins from 2.5. For that reason, instead of using an open interval at 2.5, we use a closed interval at 2.5. So, in terms of interval, we have a left closed interval, left closed, this is left closed interval, and right what? Open interval. We have a left closed interval and a right open interval. Since this interval is one side open and the other side is closed, this is called a half interval or half open interval if you like. You can call this half open or half closed, no problem. For the third example, we have 3x plus 2 less than or equal to 1 plus 2x. So let's solve again. We take like terms as we did before. So we have 3x, this is plus 2x to the left becomes negative 2x is less than or equal to, this is 1. This is plus 2 to the right becomes negative 2. So that 3x minus 2x is x, and that is less than or equal to 1 minus 2 is what? Negative 1. So our solution is x is less than or equal to negative 1. Like I had explained earlier, this simply means that all values of x that are less than or equal to 1 are in the solution region or the solution set. So let us represent this on a number line and see how it looks. So again, we have our number line. So recall that to the right of our number line is plus infinity, which we write as infinity, and to the left of our number line is negative infinity, which, and they know they have no end. We can't see their ends. So we have negative 1. So negative 1 is a number somewhere here. We draw a little ball above negative 1 and now decide, should our line go to the right or to the left of minus 1? We go back to the solution. X is less than or equal to negative 1. Once we say less than, all values that are less than negative 1 fall to to the left of minus 1. So we draw our line this way with our arrowhead. So this simply means that all the values that are less than minus 1 are in the solution region, on the solution set. The next question is, should this ball above minus 1 be shaded or not? We go back to our solution. We have x less than or equal to what? Negative 1. Or we just go back to the problem itself. We have less than or equal to negative 1. So this means that minus 1 is also in the solution region. For that reason, we have to shade at minus 1 to indicate that the solutions begin from minus 1. So minus 1 is the first solution to the inequality, and every other number to the left of minus 1 is also a solution to the inequality. The next thing is, how do we represent the same solution, in terms of set notations? This simply means that all values of x that lie between minus infinity and minus 1 are in the solution region. So in terms of set notations, I will simply write that x less than minus 1 and then negative infinity to the other side. So this simply means that all values of x that lie between negative infinity and minus 1 are in the set of solutions. The next question is, you must remember that minus 1 is also, a member of your solution. So at minus 1, we have to write less than or equal to. So this describes the same solution in terms of set notation. The next question now is, how do you write this solution in terms of intervals? So this is closed, at minus 1 and open at minus infinity. So we'll write minus infinity open, and at minus 1 the interval is closed. So in terms of interval notation, we have closed, half closed, or half open if you like. It's closed on the right at minus 1 and open to the left at minus infinity. So closed at minus 1 simply means that the point minus 1 is also in the solution region. Solution to quadratic inequalities. Now the general form of a quadratic inequality is ax squared plus bx plus c less than or equal to 0. It could also be greater than or equal to 0. It could also be strictly less than 0 or strictly greater than 0. Now you observe that this looks almost similar with the general form of a quadratic equation, except that for a quadratic equation we would have had ax squared plus bx plus c equal to 0. Then for inequalities, instead of equal to 0, the equality sign is replaced with any of these four ordered, other relations. The next we are going to discuss now is the steps involved in solving such an inequality. The steps include: 1. Move all the terms to one side of the inequality sign. Step 2. Factor if possible. Step 3. Determine all zeros. Step 4. Put the zeros from step 3 in order on a number line. Step 5. Create a sign line to show where the expression in the inequality is positive or negative. And finally, determine the solution, writing it in inequality notations or intervals. Well, we're not going to take 2 or 3 very good examples, to illustrate how all these steps are applied to get the solution set of our quadratic inequality. Example: find the solution set of the following linear inequalities. Quadratic, I beg your pardon, inequalities. 1. X squared plus 2x minus 15 greater than 0. 2. X squared minus x less than 12. 3. X squared minus 3x minus 10 is less than or equal to 0. So after some of these 3 examples, you will understand, fully how we go about this. So we start with the first one, which is x squared plus 2x minus 15 greater than 0. Step 1 says we should move all the terms to one side of the inequality sign. Now looking at our problem, we have x squared plus 2x minus 15 greater than 0. All the terms are on the left. X squared, 2x, and minus 15 are all on the left-hand side of the inequality sign. And on the right, we have 0. So step 1 is already fulfilled from the way the problem is given. It said move all the terms except 0. We should move all the terms to one side of the inequality. So you may choose also, if you like, to move all these terms to the right-hand side of the inequality. There's no problem. But I choose to leave all my terms on the left-hand side of the inequality. So step 1 has been checked. Step 2 says we should factor if possible, or if you like, factorize if possible. So we'll now check to see if our problem or example can be factorized, or if we can find factors for it. At this point, we must recall how to solve our quadratic equations, which we have done previously. You can check the description for the video, for the link to the videos. So we'll now check. Do we have 2 numbers that can be added to get 2 and multiplied to get minus 15? Of course we have. And the numbers are what? 5 and minus 3. Because 5 minus 3 is 2, and 5 times minus 3 is minus 15. Therefore, our problem can be factored. So we go ahead and solve as we would have solved our normal quadratic equation. So we have x squared. We'll now take this off and replace with these 2 factors, plus 5x minus 3x minus 15 is greater than 0. We go ahead to group them in pairs and factorize. So from the first bracket, we can factorize x, and we have x plus 5. From the second bracket, we can factorize negative 3, and we have again x plus 5. We check. X times x, x squared, okay. X times 5 is 5x. Minus 3 times x is minus 3x. Minus 3 times 5 is minus 15. So we are fine. Greater than what? 0. So this means that we take there are 2 brackets here which are the same. We take one, x plus 5, and we take x and minus 3. X minus 3 is greater than 0. So step 2 says we should factor if possible, or factorize if possible. And here we have seen that it is possible to factorize, and we have just done that. So step 2 has also been checked. Step 3 says we should determine all the zeros. Determine all the zeros. Now, to determine all the zeros, of this inequality, we'll simply replace the inequality sign with equality sign. So we have x plus 5, x minus 3 equal to 0. Because we want to find all the zeros. To find the zero simply means we should equate, the left-hand side to 0. So that we get the values of x that will make this inequality to be 0. We now solve. So this means that x plus 5 is 0, or x minus 3 is 0. This means that x is equal to negative 5, or x is equal to 3. So step 3 says determine all the zeros. Now for our inequality, there are 2 zeros. The first 0 is x equal to negative 5, and the second 0 is x equal to 3. Question is, why are they called the zeros of inequality? Let us see. Our inequality is what? We have x squared plus 2x minus 15. Why is minus 5, for example, called a zero of the inequality? Let us see. If you put the value of minus 5 into the inequality, we get minus 5 all squared plus 2 into minus 5 minus 15. Minus 5 squared is 25. 2 times minus 5 is minus 10 minus 15. 25 minus 10 is 15 minus 15, and that is what? 0. So when we substitute the value of minus 5 into the inequality, it gives us 0. Hence, we call minus 5 a 0 of the inequality. If you put also substitute x equal to 3 into the inequality, we get 3 squared is 9, 2 times 3 is 6 minus 15. So that 9 plus 6 is 15, and then 15 minus 15 again is 0. So x equal to 3 is another 0 of our inequality. And of course, these are the only zeros of the inequality. There are no other ones, because a quadratic expression usually has two roots, if you recall from our lessons in quadratic equations. So these are what we call the zeros of the problem. So step 3 says determine all the zeros. We have just done that. The zeros are minus 5 and 3. If you like, you say 3 and minus 5. Step 4 says put the zeros in order on a number line. Put the zeros in order. The keyword is order on a number line. Let's do that. So it's our number line. Recall, to the right of the number line is plus infinity. To the left of the number line is negative infinity. Now step 4 says we should place these zeros in order. In order simply means from smallest to the biggest. So minus 5 comes first on the number line. So we have here minus 5 and then 3 comes here. So we have placed, that we have put the zeros on the number line in order. Minus 3 and 5. Or minus 5 and 3 rather. You now observe that, having done this, we now have 3 separate intervals on this number line. And they're as follows. The first interval is from minus infinity to minus 5. So we have minus infinity to minus 5. That's the first interval. The second interval is from minus 5 to 3. We have from minus 5 to 3. And the last interval is from 3 to infinity. We have 3 to infinity. So these are the 3 intervals that we have on our number line, courtesy of the fact that we have introduced our zeros, on that line. Step 5 says we should create a sign line to show where the expression in the inequality is positive or negative. Create a sign line to show where the expression in the inequality is positive or negative. So follow me and see how I'm going to do it. To do that, I'm going to construct the following table. So we have interval. There are 3 intervals here. Minus infinity to 5 here. Minus 5 to 3, second interval. And the third interval is 3 to infinity, which we have here. And here we have the factors. If you recall, when we factorized, the inequality, we had x plus 5 and x minus 3 greater than what? 0. From here, we got the zeros of the inequality to be what? X equal to minus 5 or x equal to 3. Good. So we have the factors here, x plus 5, and the second factor is x minus 3. Recall, what we have when we factorize, or what we had when we factorize, was that the product of these 2 factors is greater than what? 0. And of course, I should point out here that when we say greater than 0, we are simply saying positive. We're simply saying what? Positive. Because from the trichotomy law, what does this law say? This law says that a number is either negative, positive, or 0. That's it. So on the number line, if a number is not 0, then it is to the right of 0, which means it's greater than 0. And that will mean it's positive. If a number is to the left of 0, that means it's negative, and that means it's less than what? 0. That's it. So our inequality says that x plus 5 times x minus 3 is greater than what? 0. So we want to now use, this table and with the sign, sign problem here to see on which of this interval or intervals will our solution set, be. So you watch. So the first interval we have is minus infinity to minus 5. Minus infinity to minus 5. And you know already by now that there are so many values between minus infinity and minus 5. Now, how we do this? I will pick, any value between minus infinity and minus 5, and check what happens. So in this case, I choose to pick minus 6 because minus 6 is between minus infinity and minus 5. So I pick minus 6. Minus 6. You are free, of course, to pick any other value between minus infinity and minus 5. You can take minus 7, you can take minus 8, whatever you take, the result will be the same. Good. So I've taken minus 6 from this interval. So I now come to the factors. Where I see x, I put minus 6. So minus 6 plus 5 is what? Is minus 1. What I am interested in is the sign. Minus 6 plus 5 is minus 1. So the value there in this interval is negative. That's my interest. Just the sign, not the value, just the sign. Again, minus 6 on the second factor rather. Minus 6 minus 3 is minus 9. Again there, the sign is negative. The next thing I am interested in getting is the product of these two signs, because this is x plus 5 times x minus 3, which you have here. So I'm interested in the product of the two signs. So this is negative. So minus times minus is always plus. Minus times minus is always plus. So in this interval, when you pick a value from the interval, this factor is negative, this other factor is also negative, but the product is positive. So we can now conclude that on this interval here, the values of our solution is always positive on this interval. We now go to the next interval, minus 5 and 3. So minus 5 and 3. So between minus 5 and 3, there are so many numbers, there are too many of them, we can't even count. So we pick any convenient value between those 2 points. I decide to pick, in this case, 0, because 0 is between minus 5 and 3. And of course, picking 0 will make life easier for me. So 0 plus 5 is 5, positive 5. So we have here positive plus. 0 minus 3 is minus 3. The sign there is what? Minus. So what is the product of the sign? So x plus 5, x minus 3. So plus times minus is always what? Minus. So the second interval between minus 5 and 3, we have minus. We'll do the same for the third interval, 3 to infinity. So between 3 and infinity, once again, there are so many values. We pick just one. So in this case, I decided to pick, let's say I pick 4. I pick the value 4 and check what the sign will be on that interval. So 4 plus 5 is positive 9. So this factor returns a plus. And then 4 minus 3 is 1. And again, that is positive 1. So again, on this interval, this factor returns plus. 4 minus 3 is 1, plus 1. So that is plus. So the product of that interval is what? Plus times plus is always plus. So this interval is positive. Now that we have gotten the signs, the behavior of our factors, on the 3 intervals, we now look at what step 6 says. Step 6 says we should determine the solution, writing it in inequality notations or interval notations. So we have that x plus 5 times x minus 3 is greater than what? 0. This simply means that, like I said earlier, that this is what? Positive plus. So now check, on which of these intervals is this product positive? We see that it is positive here and here. So here the interval is negative infinity, and what? And 5. It is also positive on the interval 3 and infinity. So it means that the inequality is positive on 2 intervals, and we'll bring them together with the union sign. So we simply say that the inequality is positive on the interval minus infinity to minus 5, union 3 and infinity. And what you have here now becomes the solution set of the given quadratic inequality. What this implies is that any value that we pick from this interval or both of the intervals, the value will always satisfy the inequality. Let us just check very quickly. Let us pick one from this interval and see what happens. So let us pick minus 6 and see if it satisfies the inequality. So if we pick minus 6, we have minus 6 all squared plus 2 into minus 6 minus 15. Let's see what we have. This is 36 minus 12 minus 15. So 36 minus 12 is 24 minus 15, and that is 9. And 9 is clearly greater than 0. And if we pick another value from the second interval, let's see, we pick 4 and check. We shall also observe that 4 also satisfies the inequality. So lastly, we can also represent our solution on a number line if we so please. Let us see how it looks like. Remember, to the right is plus infinity, to the left is minus what? Infinity. So the first one is We have minus 5, the zeros, and we have here 3. So this one says between minus infinity and minus 5. So 0 from minus 5 rather towards negative infinity. That is what represents this first interval. The second interval is from 3 to infinity. So from 3 to infinity. So how do we know if we should shade here or not? Is to go back to our inequality and check if it was strict or not. We go back. The inequality is greater than 0, not strict. Therefore, we cannot shade, the balls. Likewise, from the notations here, the intervals are both open intervals because the inequality given to us is not, or rather was a strict inequality. We'll now take another example so that we understand better. So example 2 says we should solve x squared minus x is less than 12. We shall solve this one now a little faster. So step 1 says we should take or move all the terms to the left or to one side of the inequality. And in this case, I have x squared here, I have minus x, so I choose to move 12 to the left. So I'll now have x squared minus x minus 12 less than 0. Step 1 has been checked. Step 2 says we should factorize if possible, or factor if possible. So we check. Are there two values that can be added to get minus 1 and multiplied to get minus 12? You think for a second. I guess they are minus 4 and plus 3, because minus 4 plus 3 is minus 1, and then minus 4 times 3 is minus 12. So we can factorize. So we now write x squared minus 4x plus 3x minus 12 is less than 0. We now factorize. So we put them in brackets. So in the first bracket, I can factorize x, and I have x minus 4. The second bracket, I can factorize plus 3, and I have x minus 4. I always love to stop and check if I'm correct or not. X times x is x squared. X times minus 4 is minus 4x. 3 times x is plus 3x. 3 times minus 4 is minus 12. That's correct. Less than 0. So this gives us x minus 4, x plus 3 less than 0. So step 3 says we should determine all the zeros. And I explained already that to get the zeros, we simply equate, our factors to 0. So we simply have x minus 4 rather, and x plus 3 equal to 0 to get the zeros. So this means that x minus 4 is 0, or x plus 3 is 0. So x is equal to 4, or x is equal to negative 3. So these are the two zeros, of our quadratic inequality. The next step says you should do what? You should put the zeros in order on the number line. So our number line is drawn this way. Here is infinity. To the left is minus what? Infinity. In order, minus 3 should come first. So minus 3 comes first, then 4 comes next. So this divides again our, number line into intervals. And the first interval there is minus infinity to minus 3. Second interval is minus 3 to 4. And the third interval is 4 to infinity. The next step says you should create a sign line to show where the expression in the inequality is positive or negative. We now do that using the kind of table we used in the previous example. So we have our interval, and there are 3 intervals here. First one is minus infinity to 3, minus 3 to 4, and 4 to infinity. And the factors we have are here: x minus 4, x plus 3. And of course, our product is x minus 4 times x plus 3. So we now check what happens, on these intervals. So in the first interval, like we did before, between minus infinity and minus 3, we pick up one number. So minus infinity and minus 3, we pick up, let's say minus 4, no problem. So minus 4 is minus 8. And our interest is in the sign, not the value, minus 8. So on this interval, we have minus. And then minus 4 plus 3 is minus 1. So on this interval, we have minus. Minus 4 plus 3 is minus 1, so it's negative. We now want to get the product of those two signs. So minus times minus is always positive. That's that. Second interval, from minus 3 to 4, we pick up one number 2. So I pick up 0 for convenience. since 0 is between minus 3 and 4. So 0 minus 4 is minus 4, negative. 0 plus 3 is 3, positive. And the product of minus and plus is absolutely minus. On the third interval, the same thing is done. Between 4 and infinity, we pick up one value. So I pick 5. 5 minus 4 is 1, and that is positive 1. And then 5 plus 3 is 8, positive 8. So that the product of the two signs, plus times plus, is always what? Plus. So with this, we are set to write down our solution set. We go back to what we had. X minus 4 times x plus 3 is less than 0. And less than 0 simply means negative. Negative, that's minus. So now come back to check where this product is negative. This product is negative only here. And what interval is that? Minus 3 to 4. So the interval minus 3, 4 is the only interval where this product is less than 0, or if you like, where this product is negative. So the only solution set, to the inequality, to the problem given to us is minus 3 and 4. The next question is, should this interval be open or closed, or half open, half closed? We simply check, we look at the problem given to us. It was strictly what? Less than 0. So the interval has to be open. On the number line, we could represent this as follows. Minus 3 is here, and this is 4. So the solution set is between minus 3 to 4. So we open our ball above minus 3 and open another ball above 4. These two balls will not be shaded because inequality given to us is a strict inequality.